Okay, guys, I think we can start the session. Okay. So last class we have been discussing about the topics which is Docker and continuous integration. So in Docker we have seen demos using ROS 2, and we have seen how to take the GUI. We talked about Rocker, which is a tool from Open Robotics, and we also talked about continuous integration. We have seen a demo repository. Okay, so these are the things that we have seen yesterday. So today we are going to discuss two new topics, which is ROS2 SLAM and ROS2 controllers. Okay, so I think you are already familiar with the SLAM, simultaneous localization and mapping, which is the package that we have been using for doing SLAM was gmapping. Okay, I hope you remember the gmapping package. Gmapping. Okay, so this was the popular package that we have been using for creating 2D map, and we also seen Cartoslam and Cartographer. Okay, so this was in ROS 1, and in case of ROS 2, if you want to do mapping, one of the popular package that is available is SLAM Toolbox. Okay, so the SLAM Toolbox is also available in ROS 1, which is also ported to ROS 2. Okay, so SLAM Toolbox works similar to the gmapping. We have to configure the package and then the node, and then it will be working it will be start working and creating the map. Okay, so before starting with the SLAM Toolbox, uh, I would like to start a demo for the SLAM. Yeah, I just want to start with the demo, so it will be easy to understand what is going on. Okay. Okay, so just search about SLAM Toolbox ROS 2. You will get multiple multiple tutorials. Okay, and there is one video as well. Several videos are available. So this is one tutorial that you can use to run the gmapping or like the mapping technique in ROS 2. Okay, after showing the demo, we will be explaining what it is. Okay. Okay, so the robot that we are going to use is Turtlebot 3. Okay, and let me start the uh, the Turtlebot 3 simulation. Okay, so one second. So I'm starting the Turtlebot 3 world, and okay, so let it come. Yes, so the simulation is here. Now I'm starting the navigation launch file. Okay, I will show you why I need to start it, or why I am starting it. And I'm starting the SLAM Toolbox, and I'm starting the RViz, and I'm just loading one configuration for navigation. Okay, it is there with the nav2 bring up. Okay, so this is what you can able to see initially. Okay, so if you remember, while we are doing the gmapping, what we were doing is like we will start the gmapping, and using the teleop we will be driving the robot and saving it. Okay, so it is easier to do the teleoperation. It's not easier to do the teleoperation, but if you start the navigation stack along with it, it is very easy to map. Maybe I can show you the demo. I can give an unknown goal position here, and the robot will start navigating. Okay, you can see here, or maybe I can put a goal here. Let me see. Yeah. Okay, so it is navigating to an unknown point. Okay, so you can see while we are navigating, it's also running the mapping. Okay, I think we have tried this kind of configuration in ROS 1 as well, like running the navigation and gmapping in parallel. So what happening is that if you remember, in order to run the navigation stack, you need to run AMCL, right? AMCL node. So AMCL node is for the localization. So you can do the localization using SLAM as well. So currently what we are doing is we are running the simulation, then we are running the navigation, and then the SLAM. Okay, so better will be taking the RQT for an understanding, so you will get to know what is happening with the node level. So I'm just taking the node graph, so just to understand what is going on. Yeah, so there are a lot of process happening here, guys. On the left side, yeah, so here you can see the SLAM toolbox. The mainly the SLAM algorithms taking the laser scan and odometry. Okay, and we have the BT navigator, which is the navigation stack 2. Yeah, so these all are the navigation stack, and we have the behavior trees, all this stuff. Okay, so mainly if you take the SLAM toolbox alone, you can see it is getting the laser scan. Okay, and it is actually pushing the map, and also it is like updating the map. Okay, because SLAM, if you run the SLAM algorithm, it is creating the map, right? So for example, if I'm giving a goal position here, the robot is trying to move, and it is moving to that, and automatically it is completing the map. Okay, and if I'm giving the goal position here, it is moving to that, and there are some area that we need to fill it up. Okay, and on the left side you can see the navigation to panel, which is having the status of the life cycle node. Okay, I mentioned that the navigation stack 2 is actually running different life cycle nodes, and the status of each life cycle node, which is navigation, feedback, all these things is mentioning. Localization is not running, it is handling by the SLAM itself. Okay, so this is a demo I just want to show you. Basically it is the same as the G mapping, but maybe I can show you the main differences. Okay, and it is like, I will say it is working pretty smooth. There is no localization problem. In G mapping, we were getting a lot of issue with the localization. Sometimes the robot will be drifting, but here it is pretty smooth. Okay, so let me close all this stuff, and let me take the tutorial that we have to follow. Okay, yeah, so before starting, I just want to just sharing the repository of SLAM toolbox, and there is a talk from Steve Mackensky. He is the author of SLAM toolbox. Okay, and here is the node graph. Not node graph like architecture, what is inside it, what are the inputs, all this stuff. So I just want to explain about why we need to use SLAM toolbox in ROS 2. So there are several reasons for that, why we need to choose. So maybe the cartographer is available in ROS 2. Gmapping is not available. It is only available with Isaac SDK packages. So SLAM toolbox is not only just doing the mapping and localization. It can be used in like a product level. It can be used in a product. What I'm mentioning is that this product or this project actually started by Steve, and he created this for a product. Okay, he actually tested in a very big environment. So the problem with the Gmapping is that if you are working with a big environment, the mapping accuracy will not be that great. And there is a thing called loop closure. Like it's mainly like when the robot is actually going from one place to another, and if it is returning, like it is closing the loop basically. Okay, so there are few SLAM algorithms in ROS is supporting the loop closure. Like if you take Hector SLAM, it is not having the loop closure, but like Gmapping is having loop closure, and CartoSLAM is what is using in the SLAM toolbox, CartoSLAM. There are a lot of improvement in the CartoSLAM, and not only that, not only the loop closure. One of the advantage of SLAM toolbox is that we can resume the mapping. Okay, we can resume the mapping. For example, if you are doing the mapping of a big area, then you can add these maps. I mean, you can save the map and do the mapping later. We can expand the map. Okay, so there are different capabilities in SLAM toolbox, but by default what we are using is we are just mapping it and saving the map. So that is what we are doing with the SLAM toolbox, like the Gmapping. Okay, but there are many things that we can do with SLAM toolbox. Okay, and yeah, so that is the benefit. So first was like it is having loop closure, and also it is very very effective compared to Gmapping, cartographer, and other SLAM algorithm, 2D SLAM algorithm in ROS. And you can do the like you can it's you don't need to do one-time mapping. You can do one by one. You can stitch, you can serialize each map, and you can resume the mapping operations. Like that is a good feature, right? Like if you are going to map a big area, we need to sometimes we need to pause, right? So there should be some functionality to pause and stitch the map. Okay, so SLAM toolbox is having that feature. Okay, and basically if you take the node, it doesn't have much stuff. Like you can see here, it is mainly subscribing the scan. Okay, and it is subscribing I mean it's publishing map and post. Okay, and there are some services that actually it is exposing. So services are like if we want to, I mean that's what I mentioned. In order to do the saving of the map, then posting it, then serializing, resetting, all these things can be done using these services. So that is the main difference that I am seeing with Gmapping package and the SLAM toolbox. Okay, so the main input is, I think it is scan and the TF, I guess. Okay, so these are the main inputs to the node, and output will be the map. Okay, yes. So if you check the structure, it is having a lot of blocks compared to the gmapping. Gmapping was just a single node. This is also single node, but which is having multiple plugins and all in order to enhance the capabilities. So here you can see the SLAM toolbox requires LiDAR, and also I think it need the odometry. Okay, so that we can check in the launch file what are the nodes and what are the parameters, and like it is just a second, there are several processing happening. There is a thing called GraphSlam. I mean, that is actually the one of the technology that we can use to used in the SLAM algorithm, GraphSlam. So it's basically creating graphs or nodes for this. So currently for the SLAM toolbox also it is creating different nodes, okay, while the robot moving. I can show you the nodes, by the way. Maybe after explaining this I can show you the nodes in RVist. And basically like any other SLAM algorithm, it is doing the scan matching, then it is checking the loop closure, and this one is one different module which is optimizer. So that is not there in gmapping. So what I am trying to say is that when we compare to the gmapping, the existing SLAM packages, this is, I will say, much robust because it is having a lot of stuff to do accurate mapping, and it's reliable. Like if we are planning to work with an area of like 20,000 square feet, more than that it can able to work, and it is having the loop closure as well. Okay, it can only do the 2D SLAM. Okay, so that is one thing to note. Yes, so now I just want to go to the repository. Yeah, this is the repository, I think. Yeah, so you can see here there are some configurations of SLAM toolbox like odom frame, map frame, base frame, scan topic, then yeah, then the regular stuff that we have done that we have seen in gmapping. Okay, so these are some configurations. I mean, there are many configurations, by the way. So the configurations are given, and I just want to check the launch file. So in SLAM toolbox, inside it there is a launch folder, and there are some existing launch files. Okay, so we are running the async launch. Okay, so basically the SLAM toolbox can work offline and online. Online means the robot is working. Offline means maybe we can we have the data and you can build the map, something like that. So if it is offline, I think we can do with synchronous mode, like all the sensors at the same time. I think the online async is what we have performed, okay, while working with the Turtleboard. So if you check the launch file, this launch file is simply running the node. That's it. That is the main thing. Okay, so which node is it running? Inside the SLAM toolbox, there is an executable called async SLAM toolbox node. Okay, it is simply running it. Okay, and this node is actually a lifecycle node. Lifecycle node I already explained. The lifecycle node, you can start, stop, then pause. Okay, it's not like the regular node. Okay, and if you check it, that's all actually. Like we are simply starting this node, and we have the parameter file as well. So if you check the parameter, yeah, so here the SLAM toolbox mapper parameter. So as simple as the gmapping, we need the YAML file for the SLAM parameters and just starting the node. That's it. So the parameters are in the config folder. So if you just check mapper online async, these are the parameters that we need to tune. Okay, one second. So you can able to see the solver plugin. I mean, there are some optimization plugin. So unlike gmapping, gmapping is a single node, we can't do much things on it, but in SLAM toolbox we can configure a lot of stuff. Okay, and the regular topics, the scan topic, all this stuff, and there are some similar parameters like the gmapping. Okay, use scan matching, do loop closing, all these things. You can see this, some of the important parameters. Okay, so I mean, if you take the SLAM toolbox, it's simply running a node with this configuration. Okay, and make sure that you are feeding the right inputs. Basically the ODOM, we have to mention the ODOM frame, map frame, then base footprint, scan. I think that's it. Okay, if these things are okay, then I think we can start the SLAM toolbox. And there are two modes actually, like you can do the mapping or you can do the localization as well. Okay, so you can use this node for the localization as well. So that is the double benefit of the SLAM toolbox. You can change the mode. Okay, so these are the basic features of SLAM toolbox, and I can show you the demo again with some other stuff. Okay, one second, let me start the simulation and let me delete all this stuff. One second. Okay, we started again the simulation that we have started, and we are starting the navigation. Okay, now we are starting the SLAM toolbox. You can see the launch file here. I didn't create any new launch file. You can simply reuse the existing launch file from the SLAM toolbox package itself. Okay, and now we can start the RVs. Okay, simply loading the configuration of navigation. You can see it is from the nav2 bring up, RVs nav2 default view. Okay, I'm just starting it. Okay, so you can see the navigation bar here. Okay, maybe I can put here, and there is a panel for SLAM toolbox. Okay, that is again an interesting thing. It is slightly complicated, but I can show you the basic working. So you can go to panel, add new panel, and SLAM toolbox plugin. Okay, so this is the panel that you are getting for the SLAM toolbox. Okay, so what I will do is I will be ticking the interactive mode. Okay, these two things, and instead of waypoints I will be selecting this SLAM toolbox graph visualization. I mentioned that this is SLAM is based on graph SLAM. It is creating set of nodes. I'm not very expert in that specific area, but I know it is creating a set of nodes, okay, for saving or creating the map. So what happening is that I just added the marker array topic as SLAM toolbox visualization, and I am just creating an interactive marker display type and putting the topic or namespace to SLAM toolbox, and I am starting the navigation. So you can see it is creating a set of nodes. You can able to find. One second guys, let me close this. Okay, yes, let me give another goal position. Okay, yeah, so you can see the nodes actually created by the SLAM toolbox. So these nodes, I think the importance of this is that if you want to resume the mapping and all, these nodes will be helping. Okay, we can align with these nodes and we can do it, but I'm not very I mean the GUI is somewhat tricky. I tried with some features, but some features worked, some features not. Maybe it my problem, but you can find it. You can find the nodes, and you can also make it interactive. So the reason why we need to make the nodes interactive is we can align if we want to resume the mapping, we can align the robot to some nodes, and then we can start mapping and we can save that map or serialize that map, like, and we can add the submap later. Okay, maybe I can explain that. So this is one thing that you can see. You can visualize these nodes from yeah, and once you have created or completed the map, you can either save the map using map server, or there is an option here. You can simply put the map name and you can save the map. For example, I'm just entering my name and I'm just saving the map. So it will be saving in the position where I took the terminal mostly. You can see the map. Okay, and the YAML file. Okay, yes, and you can also do the serialization of the map. So I will explain that maybe in next class. Like I am also a little bit confused in that. So like if you do the serialization, you can serialize that map in a different format. Okay, maybe you can see here. It's actually not saved as PGM file. PGM file is the final product. Okay, it is saved as postgraph. Okay, so these postgraph can be used later for maybe stitching the map. Okay, like imagine this is just a section of the map. Okay, so if we have the postgraph, we can merge these map to the existing map. Okay, so um, um, I can also do a trial for that. Like there is an option called merge map tool. Maybe I can do one trick. Maybe I can restart the map, everything, and I can try the merging of the map. Let's see how it works. So I started the simulation, and so you can either start the simulation and start the async, and you can use the teleop to do the manual teleop, but I will prefer the navigation because it is easy. You don't need to move the robot here and there. You can simply run it automatically. Okay, like an autonomous exploration kind of stuff. And starting. Okay, okay, Now I'm just adding the SLAM toolbox, and I just saved a serialized a map called Lentin1, which is a complete map. So let me try whether it work or not. I'm just giving the name and then add submap. Let me check if there is any. It's showing merged maps failed to load postgraph from file. 1 second. Let me just give the complete path. It seems like, yeah, it is not doing anything. Maybe I can give the map itself, the complete map. Yeah, that is also like, so it is trying to load the postgraph file only, but it is not loading, by the way. Okay. Yeah, so that's why I mentioned like the GUI is slightly confusing, especially the merging. But the
Sorry, sir. Hello.
yeah, Kasim, tell me.
Yeah.
You work on
I think
this?
maybe, yeah, a little bit, not that much. I
Okay.
think this is for example, you have a very huge environment, and you have, for example, 2 or 3 robots, and they are making, for example, one robot uh, do some slam on one part, second robot is doing on second part,
Yeah.
then you can merge in one map like that.
Yeah, but in this case, what I did was like currently we only have this much of map, right? And we have saved the full map as well. Okay, so what I am thinking is, what about merging this map with this map?
I
Okay.
think it's not possible. I think this is for both the map which are in continuously, I think, working.
Uh,
Maybe my opinion.
okay, but I have seen in the website. Okay, in the website I have seen they are doing with single robot. Maybe I can show you that. 1 second. So there are some gif gif file. So here you can see a single robot is doing it. There is no multiple robot, but I mean we can do with multiple robot and also single robot. Like you can, even if you are doing with any number of robot, if you have that map segment, you can stitch it. Okay, so here they are doing with single robot, and they are not demonstrating the stitching part. But I was just trying, like currently if we want to add a submap, I can simply add this submap, and maybe uh, I can press the generate map. Then I am expecting the complete map to be done. So but uh, it's showing failed to load post graph. Okay. So maybe I think, I'm not sure the service is running or not. Maybe I can check the service list for merging. I think SLAM toolbox. Okay, add submap is there, but unfortunately I think from the UI at least it is not working currently. Like what happening is that if you are pressing each button, these buttons are invoking some services. Okay, and these services will be contacting the SLAM toolbox node. Okay, so you can save the map that we have already tested, serialize the map that we have tested, deserialize the map that also working. I mean, it will be doing something, but I'm not sure. So these two things from my experience is working, and also this interactive interactive I mean mode is also is working. And also we can change the mode to localize, I guess. Okay, so it is somewhat like I couldn't find good documentation. There are some documentation in the website here. There is a section here, and they are explaining about this, but not that in a good level. Here you can see they are took some old screenshot. There are three things here: interactive mode, accept new scan, and process scan. But now there are only interactive mode and accept new scan. Okay, okay. Next class I will be showing that. Let's see whether I will get good information about it. Normally, for just creating a map, I usually don't use this plugin or this plugin. We can simply map it and then we can save the entire map. That is the workflow that we are commonly using. But I just want to highlight this plugin also. There is a plugin in which we can do these things. Okay. Yes. So that is about the SLAM toolbox. It is very easy to configure and run. Okay. And I just want to show you one visual SLAM as well. So configuring a SLAM for your robot, it is pretty simple. If you have the ODOM and the regular stuff, the odometry, laser scan, and if you already run the G mapping on it, it will be working with this SLAM toolbox. Okay. So this is only the vSLAM that I have seen. I mean, this vSLAM is much active. I mean, it is having good community, but it is an NVIDIA product. But I think I have seen some demos of these vSLAM when I was in NVIDIA HQ. The engineer showed to me some good demonstration and it is working good. So I just want to suggest these vSLAM, which is Isaac ROS Visual SLAM. We need the Isaac packages to, I mean, the NVIDIA hardware to set it up. And basically, yeah, so we can feed wheel encoder, LiDAR, and the stereo cam for the vSLAM. Okay, so along with the wheel odometry, we can have the vSLAM for the navigation. Okay, so they have mentioned about some benchmark. Okay, I didn't try this yet, but there are good examples here to set this package up. There are, yeah, I think the tutorial is straightforward. Mainly, like, we need to provide the images as the input. So these are the topics that it is subscribing. Like it is expecting the stereo cam, so left image, right image, then also expecting the IMU data. So if you feed it, it will be giving the odometry. Okay, so that is what the vSLAM is. Yeah, maybe if you have an NVIDIA board or NVIDIA GPU, I guess you can try this. Unfortunately, I'm trying with the VMware, so they are also showing some demo of the vSLAM. But the good thing is that, like, we will get the odometry. I mean, if you have multiple source of odometry, it will be good for the navigation, right? So vSLAM, I think they actually benchmark with OrbSLAM, which is again a vSLAM available. Maybe, yeah, OrbSLAM 2, but I just want to check whether it is ported to ROS 2. Okay, that also I need to check. Currently this is an old one. Maybe I can check OrbSLAM ROS 2. I didn't check that yet. Yeah, it seems like someone implemented it. Let me see. Yeah, there is a ROS 2 port. Maybe I can share it. I think this is not an official port or something, but some companies done that. OrbSLAM is again a visual SLAM, but when we compare with, so this will be running in most of the PC. Okay, we have to feed the input is obviously the image. So we can do with the mono image as well. Like if you have a single image, you can do the VSLAM, and also if we have the depth image, you can do we can do with the stereo. So that is one advantage with OpsLAM. Okay, OpsLAM will be working with different device, but in case of ISAC, I think it is mainly preferring the stereo. Okay, and they have just compared the performance as well. So if you check the OpsLAM 2 and VSLAM by NVIDIA, I think it is accurate. The VSLAM is pretty accurate, and the runtime, the speed is much higher in VSLAM. Okay, and the translation, I think it is the error or something. I need to recheck, but in total, if you check, the VSLAM is better for, and also they mention the frame rate that we can able to run, like 228 FPS, 127. Yeah, it is pretty good. There is a demo here. Yeah. Okay. Yes, so you can keep in mind, I mean, OpsLAM ROS 2 and NVIDIA ISAC Visual SLAM. I was only planning for Visual SLAM because that is the latest one, and there are we are getting proper support from NVIDIA. And OpsLAM 2, it's a community driven code, so I'm not guaranteed the performance and also the maintenance. Okay.
Excuse me.
Yeah. Kasi.
Sir, how about do you like NVIDIA Isaac Sim?
Yeah, so the problem is that, Kasim, I can't able to run the ISAC in my PC because I have 1050 GPU. So I have seen some demos. I got some demos from the NVIDIA as well. So as of now, I am impressed with the realistic simulation. Okay, and also the packages. But yeah, I mean, they are actively developing it. So why you ask, Kasim? Do you have any opinion about or specific things about NVIDIA Isaac Sim?
No, actually, then go to hardware, it will be some bit difficult when you
Okay.
implement not a real hardware.
Okay. So
Because when you just simple, for example, ORB3 Slam 2, I think it's available, ORB3 Slam 2. Maybe last time I checked, or those two.
okay.
So
So
it's very light than Isaac's Visual Slam.
yeah. So when coming to the hardware stuff, I will say, like, I am preferring Isaac Sim for, I mean, mainly for the simulation, obviously, but you can connect the Isaac to the hardware as well. I mean, there are certain demos from Franga Robot. They have done the simulation and transferred to the hardware. Yeah, so I think we can able to run using ROS 2. We can interface using ROS 2, but I'm not sure because I didn't have much expertise on it. I couldn't able to run it on my PC first. So mostly I need to upgrade my PC. Yeah, so that's what I'm planning to. I am really planning to learn new stuff. So yeah, so that's it. I think there are, yeah.
One more thing I want to add that last week Stu McKenzie and NVIDIA collaborate. They make us some
Yeah.
a movie.
With
Yeah,
with the
you
NVIDIA,
heard
right?
about it. Yeah.
Yeah. So the thing is that Steve is already visiting NVIDIA HQ for the navigation too. Like the Isaac Sim or Isaac is like tightly integrated to the navigation stack. So Steve is there for like integrating this. Okay.
Okay.
So that is what I have got from the engineers. Okay,
Okay.
so
Sir,
yeah,
out of the course, sorry, I will take 1 minute more.
yeah.
Are you joining the IROS this year or anybody in our group? IROS
Not
2024.
me mostly, not me. Maybe some other people will be. Maybe we can put a, uh, comment or something in the group, and let's see how many of
If you
come.
want to join, then most welcome because it's happening in Dubai.
Oh.
Yeah.
Okay, okay,
And
okay.
next week, I will join that group.
Oh,
I am joining Khalifa University
okay,
Dubai.
okay. Great,
Yeah.
great.
So I will be their team
Okay.
organizers, IROS organizer.
Oh, okay. That is great.
Yeah.
Great.
Uh,
Okay, so
so I think if you have time or in the group, so we can make, I think we have 1 week for the submission of paper.
okay.
So we can collaborate and make a good paper in the group if anybody agree.
Okay, maybe we can put a message in the group and let's see if anyone interested because I don't know, I'm not sure about my thing because I am already in the projects. So not sure I will get, but you can put a message and let's see if
Sure.
anybody. Okay. Okay.
Okay, thank you.
So yes. So now we can jump into the next topic, which is one of the important topic. I am planning to discuss that with an example. Okay. So the topic is ROS2 controllers. Okay, ROS2 controllers. So the advantage, not advantage, like the good thing about the ROS2 controller is that the documentation is pretty good and we have a lot of demos available. Okay. So if you remember the ROS controllers, I think you remember the ROS controllers, right? So basically, like in order to move a joint, okay, in order to move a joint, we need to assign a controller in the joint, and we are feeding the joint position to the controller, and the controller will be, uh, controlling the joint value in simulation or in the real hardware. Okay, so if you simply search for ROS controllers, okay, so yeah, ROS controllers, you will be getting the ROS 1 controllers. Okay, I hope you remember these diagrams. Like we have a controller manager which will be loading each controller, and there is a hardware interface layer which is for connecting the controllers to the external hardware. Okay, so this is how the controller ROS control package. It's not only one package, it's a list of packages which include the controller manager and list of controllers. Okay, there are many controllers available. There are like differential drive controller, then trajectory controller, position controller. So there are different kind of controllers in ROS. Okay, so you can see some of the controllers from here, and also if you check this, maybe I can share the link. This is for the ROS 1, by the way. You can see this much of controllers are there. Okay, so what is controller doing? So these controller programs are doing different stuff. For example, the differential drive controller, what it is doing is that it is subscribing to command velocity. Okay, and it is converting the command velocity into motor speed. Okay, motor speed, and it is also generating the odometry. Okay, so this is the popular controller. Like whenever you use or whenever you create a differential drive robot, mostly you will be using diff drive controller. Okay, so there are two options that you can do for controlling a differential drive robot in simulation. You can either use a differential drive plugin from Gazebo. Okay, that is actually different. It's actually a plugin from Gazebo, so it will be only working with the simulation. Or you can use the diff drive controller. So which is the actual controller which can be used in simulation as well as the actual hardware. And if you just check, we can see a set of controllers like joint trajectory controller, which is mainly using for controlling the robotic arm. Okay, you know what is a trajectory is, right? So it is having a set of points, and you can able to control it. Then there is position controller, velocity controller, effort controller. Inside the effort controller there are effort controller position. You can see all these things from this link. Okay, so there are different types of controller, and most of these controllers are ported to ROS 2. Okay, ROS 2. And let's check the website of ROS 2 control. Okay, so you can imagine the ROS 1 control is ported to ROS 2, and with some good things. Okay, like any other packages like nav2, move-it2, they added some more stuff. Okay, so this is the official documentation of ROS 2 control. And like the ROS 1 control, you can able to see the packages like ROS 2 control, which is the main package, and inside that we can see ROS 2 controllers. Okay, this package contain different controllers. Then controller toolbox, this is for like implementing the PID tuning and all. Then real-time tools, like if you want to work with the real-time operating system, you can use some tools from it. Then control messages. Okay, and the important package that we need as a student, we need is the ROS 2 control demos. Okay, so I didn't see this much of demos from any packages. Okay, so what's going is that like you can see all the demonstration of different controllers from this package. Okay, so you can see different examples. Okay, if you click it, you can able to run it. Okay, so before entering to the demos, first let's see what is actually ROS 2 control and how we can install it. Okay, and after that we will be seeing the architecture a little. Okay, so installing ROS 2
Sorry, sir.
yeah.
I'm disturbing again.
No problem.
Sir, when controlling, actually I'm a control engineer.
Yes.
So coming to controller, then I always say PID, LQR, MPC, MPPI, like that controller. So where that controller comes here?
Yeah.
In this.
Yes. So actually,
You got my point, right?
Yes. So So I can explain that. So the thing is that I am actually mentioning about the controllers that is inside the ROS 2 repository. So if you just check the ROS 2 controllers, you can able to see the available controllers in ROS 2 controller package. But the controllers that you mention is all, I mean, it's all belongs to controllers only, but it is not included in the repository, unfortunately. Okay, so I think these controllers will be adding to the main repository soon, but as of now these are the controllers that is available. Okay, so that is the thing, Kasim. So what you said was correct only, but I was talking about the controller package, I mean the official ROS 2 controller package, and you can find other packages maybe from some external repository. Okay, not from the official repository, maybe from some external repository. But so that is the thing, like you can find other implementation not from the official packages, Kasim. Okay, yes.
Okay, sir, but I think that is very important. I think why they are not included.
Yeah. That is true. That is actually true. I think all these packages are like it's all evolving, right? So hope somebody will be contributing these controllers to the official branch soon. We can hope that, because there is a lot of work to do, right? Okay.
Sure, sir. Thank
Yeah,
you.
yeah. So yes, so what Kasim mentioned was correct only. Like what he is saying is that like there are lot of type of controllers available, and why I am not mentioning this controller, because officially ROS only have these much of controllers, but we can hope there will be more controllers will be adding or contributing by other developers. Okay. Yes. So coming back, if you just check the website, installing of ROS2 control is pretty easy. Okay, so I can show you the installation. So what they are showing is how to set up the ROS2 control package from the source code. Okay, so this is the instruction to do that. But obviously we have the Synaptic Package Manager, so it is easy, like ROS2 ROS humble control. Okay, you can simply search it and you can find all these packages, the binaries. Okay, so you can find the controller manager, the controller interface, control toolbox. Okay, so you can install all this stuff to make the to get the controller. Okay, controller packages. So 1 second. Yeah, I think these are the packages that we mainly need: the controller toolbox, controller interface, controller manager. Then another package we need is Gazebo ROS control. Okay, if you want to interact with Gazebo Classic, you need the Gazebo ROS2 control. Okay, and Gazebo ROS. So there is another thing called Gazebo ROS2 controller demos. It's already there. Okay, there are some demos already there, but we will be running the ROS2 controller demos. Okay, so there are a lot of examples available in the website to learn the ROS2 control quickly. Okay, now going back to the architecture, it's almost the same, but there is a difference. Okay, that's actually a good add-on, I will say. Okay, I will say what it is. So if you want to load the controller, the controller manager is the program which is loading this controller against each joint. Okay, for example, if you are loading the joint trajectory controller, what it does is that it will have what are the joints that it is going to control. Okay, so the controller manager will be loading the controllers, and these controllers are interacting with the resource manager, or the controller manager is interacting with the resource manager. So what is this resource manager? The resource manager we can also call a hardware interface. We already seen. So this part is actually little confusing for ROS1. Okay, this was actually confusing for ROS1. So most of the people don't know, like after assigning the controllers, how to how to get the controller commands to the hardware, and how to get the feedback from the hardware. Like imagine if you want to control the robot in the simulation. Okay, so the simulation will give you the functions to write the join values. If you want to move a join, the Gazebo APIs is there to write the join values, and the Gazebo APIs are there to read the join values. Okay, but what about a real hardware or real joint? There should be some part in which you can able to get the controller data, and we can able to write to the motor or the servo, and the feedback, like if you are just if the controller is giving like 80 value called 80 or 100, when the actuator is going to 100, it should give the feedback back to the controller. Okay, then only the controller can work. So the resource manager is also, maybe I can call it as a hardware interface. The main duty of resource manager is to interface into different kinds of hardware. Okay, when the robot when the robot works, the controller will work on each joint, and the joint values from the controllers and the state of the controller, joint state of the controller, is actually going through the resource manager to each system. Okay, there can be different kinds of system. System means like there can be a joint, there can be a motor, there can be a sensor. Okay, sensor will only have the state. Okay, like it will be simply publishing the value as a state. Okay, there is no write, only read. Okay, and there are thing called system. Okay, system is nothing but a complex robot or a complete robot. Okay, which is like having different joints and all. So you can see here on the top part of this architecture, we can see the controllers. Bottom part, we can see the hardware interface mainly. Okay, and the hardware interface can able to read commands to the hardware and write commands. I mean, here is reading and here is writing. Okay, and these are the different hardware interfaces that is available. One is sensor, system, actuator, and GPIO. Okay, there are several types of hardware interfaces available. So if you want to completely control a robot, maybe you can use system hardware interface, in which you can directly write the joint values and get the joint state. Okay, if you only have one actuator or something, or one motor, you can use the actuator, or you can individually assign actuator hardware interface to multiple joints as well. If you have any sensors like temperature sensor, IMU or something, you can use a sensor hardware interface to update the state of it. So this is actually the
Sorry, sir, I have a question here.
Go on.
So here, this is for entire different systems, not right, not one robot.
Which one? This system?
Yeah, these systems are sensors, actuators. These are of different robots, not one robot.
You can include for one robot as well. Like what the system hardware interface is saying is that it can able to control a list of joints. Okay, and maybe you can add a sensor to it as well. Maybe when we discuss the example, we will get the exact idea. I can show you what are the
Sorry, in simple word, for example, the above part, controller 1, controller 2, controller 3.
yes,
This is, for example, running in my PC, right?
yes,
For example.
yes,
And then below part, this is hardware.
yes.
For example, my
hardware interface, hardware interface and
hardware interface. One is my manipulator, one is my, for example, the room temperature, and third robot is, for example, differential drive robot.
Yes.
So
Yes.
3 robots.
Yes.
So we can control all this by using single this interface.
Yes. So
Right.
I can explain that. So these 3 controllers are working independently. Okay, like there is no
Okay.
dependency between these controllers. Like the controller A may be for sensor, as you mentioned. Controller B may be for arm, and controller C may be for the differential drive. So these controllers are independently connecting to a set of hardware interfaces, and it will be communicating to corresponding hardware. So all these things are independent only. Okay, so you can assign any number of controllers, and these controller can independently talk to this hardware. So you can have the control of as many hardware that you like. You can put or connect any number of hardware to any number of controllers. So that is the whole purpose, right? It is not only one robot. You can run multiple robots or multiple hardware units, okay, and we can assign to different controllers. Okay, that is actually possible, Kasim.
Thank you, sir.
Okay.
Thank you. Got it.
Yeah. So maybe after discussing the example, you will get an idea. I think explaining with example actually work. Okay. So what we have to understand is, first we have seen the installation. Second, we have seen the architecture. We don't need to check these. Okay. This is the UML class. We don't need to. What I will do is I will directly jump to the example, and then we can see how the things work. Okay, so yeah, so I'm planning to show you one example. Okay, and planning to show you an example with simulation. Okay, let me check the example that, okay, so this was the example that I have used. Okay, first I will show you the example, okay, the working, and then I will explain. Okay, 1 second. GUI equal to true. So if you see this example, I think it will be familiar to you for sure. You may have seen this robot in ROS 1, right? The RR bot, which is like a 2-join robot. In ROS 1, we have added some camera here, some laser scan, all this stuff. Okay, so what you are seeing is a simulation of RR bot, like we have done in ROS 1. Okay, and what I am doing is let me try to control it using RQT. Let me see that is possible or not. Yeah, join trajectory controller, which is not this. Yeah, not this, guys. Okay, so what I'm doing is I am simply running this example. I'm planning to control it. Okay, example overview. 9th example. So I'm just sharing the link, guys. So this much of examples are there. Okay, so this is an example for RR board without gazebo, and this is with the gazebo. So we have started this command, and now we can see one by one. So we have the simulation ready, and first what we are doing is, if you just type ROS2, you can find ROS2 control, okay, which is a subcommand. So what is control? So control says it is various subcommands for ROS2 controllers. Okay, maybe I can do like ROS2 control. So you will get the subcommands again. Okay, so maybe I can just type like ROS2 control list controller. So it will be listing what are the controllers running now. 1 second, it is controllers. Yeah, I think that is okay. So you can find there are 2 types of controllers working now. Okay, so what are they? There is a forward position controller and join state broadcaster. Okay, so I hope you are familiar with the join state broadcaster, which is basically sending the join state. That's it. So what is the forward position controller? Forward position controller is nothing but if you give the position to this controller, it will be simply setting that position to the joint. That's it. Okay, so these are the 2 controllers that is using, and it's already there with ROS2 control. Okay, and what I am doing is I'm just going to publish a value. So if you just do rows to topic list, okay, so currently there are two controllers, right? So you can able to give the commands to the forward position controller, okay. So you can able to publish the join values, and then the controller will get the input and it will be doing the controlling of the joint. Okay, so I'm just trying to do a control. I mean, the robot is actually controlling using the forward position controller. There are two joints. Okay, there are two joints. So what I'm doing is I am simply publishing the topic, and you can see this. Okay, so it is basically publishing that value, simply setting that value. Okay, and if I'm just changing to one second, you can see it is immediately setting. Okay, and what we have done, it is very simple. Like when we check the rows topic list, we have found that the topic that we can use to send the controller input. Okay, so if you just do rows topic type, you can say it is a float 64 multi-array. Okay, so I mentioned that the forward position controller is basically for setting the position of a multiple joints. Okay, it can be like one joint or like n number of joint. So you can simply give like this, like rows topic pub, forward position controller commands, then the topic, a message type, and the data. Okay, so if you do that, the controller will work. Okay, so this is the first demo I just want to show you. I mean, this is the demo that we require for a manipulator. I think this is one demo, and let me explain. Okay, I will take like maximum 20 minutes for explaining the controllers. First I will be explaining this example, and I will be showing you with one differential drive robot as well. Okay, so let's go to the rows to controller demo package. I have created a workspace, okay, called rows to control workspace, and then cloned everything into it. So you can able to see if you just take the demos, yeah, this is the set of instruction that you can use to clone the latest rows to controller demos. Okay, so I have done that, and you can find all this example, and the example that we have tried was 9. Okay, 9th example. So first, if you remember the rows 1 control, there are something that we have done, like we have added some tags in the URDF. Okay, and we have added, or we have started the control manager and load the controllers. Okay, the controllers are written in a YAML file, and it will be loading, and it will be loading by the control manager. Okay, so this is how we are starting a controller. So I can say it again. We have a URDF file for a robot, and we have to put some tags, okay, controller specific tag for each joint, and then we have to start the control manager. Okay, then only the controller manager can find the joint. Okay, so this is how it is working. So let's start with the description. Okay, description means a robot model. So if you just take the URDF, this is the main URDF, you can find you can find a set of macros. Set of macros means this sacro is included, like the basic URDF is included, then the material sacro is included, Then the control sacro. Control sacro means that sacro is having the control tag that I mentioned. Okay, and then if we want to run on Gazebo, okay, if you want to do the simulation with ROS2 control, you have to set these argument. So what happening is that if there is any if we want to run it on the simulation, then it will be adding rrboard Gazebo sacro. So what you are seeing is a sacro file which is having different sacro file included. Okay, so the first sacro is having the joins and links basically. The second sacro is having the color of the join, all this stuff. The third sacro is having the main part that we have to discuss, which is the control tags for each join. And the fourth sacro, if we want to have a Gazebo simulation, we need to start a Gazebo plugin to interact with the controller. Okay, so let's start seeing these files. Okay, so first let's see the control. Maybe we can do by one. Yeah, so in the maybe I think better to start with ROS2 control. Okay, so in this robot there are two joins, join 1 and join 2. I think you already seen it, right? So if we want to assign a controller to this joint, there is a tag that we have to use. It's called ROS2 control tag. Okay, you can add it anywhere. Okay, inside the URDF, or you can make it as modular. Okay, you can add it anywhere. And what you have to do is you have to so these tags, what is the purpose of these tags? So these tags basically loading the hardware interface. Okay, so these tags are actually loading the hardware interface. Okay, and it is also saying what are the state that we required. What is the command interface? What is the state interface? Command interface means you have seen two joints, right? So these joints are controlling by position. Okay, so the command interface is position, state interface is again position. State means the state, joint state. So that is what we are seeing first here. We have to mention the joint name, okay, and what is the command interface. So it is position, and you have to mention what is the limit of the that command. It should be within -1 to 1. So controller will get to know the limits. And what is the state? It should be in position. Okay, and that is for join 1 and join 2. Okay, and so inside this hardware tag, you have to be careful here. So what is this? Okay, so if you need simulation, okay, if you need to work with simulation, then the Gazebo Classic will be this will be setting, and this plugin will be loading. Okay, if you are directly working with the hardware, then this plugin will be loading. Okay, so you may be a little bit confused, but I can say it again. So if you want to interface to a simulator, you have to start a hardware interface called Gazebo ROS2 control Gazebo system. Okay, it's a system plugin, okay, for simulation. So if you want to start controlling a Gazebo simulator, you can simply add this plugin. Okay, but if you want to take this control to some external robot, okay, then they have already given a dummy plugin in which you can access to the position, I mean command and state. Okay, so if you have a actual robot, this is where the ROS2 controls actually looks good compared to ROS 1, because you can easily write the controller value to external robot using this plugin. Okay, and the plugin template is already given here. Okay, so I can explain again, like inside the Sacro file you have to mention these ROS2 control tag, and inside that you have to mention what kind of hardware interface that we are looking. This is a system hardware interface. Okay, because we are writing two joints, like we are using the system hardware interface, and you have to mention which plugin that we need to use. Okay, so that plugin will be handling these read and write to the hardware or simulation. So in case of simulation, we need the Gazebo ROS to control Gazebo system, which is already installed, okay, along with this package. If you only want to control the hardware, then we can use these demo dummy code. Okay, you can change everything, and there is an option to, like, there is two function, read here and write here. Okay, so you can see here, this is the part of exemplary purpose. Please do not copy to production code. Here you can write into maybe to Arduino or to directly to some motors or something, and here we can read it from maybe Arduino. Okay, read and write. That is the basic things to control hardware, right? So you can maybe publish some topics to move the motor, and here you can subscribe or something like that. Okay, so this is the important part in the ROS2 control. You have to assign the plugin. Okay, so if you do that, then the next thing is you have to start the load the sorry, you have to load the control manager and its parameters. Okay, so we have to start the controller, right? So if you're working on the simulation, you have to note one more thing. You have to start another plugin inside the Gazebo tag. I hope you remember this Gazebo ROS2 control. Okay, Gazebo ROS2 control, and you have to give the controller tags here. Okay, this is only for like if you are working on Gazebo. Okay, so I'm just repeating, like if you want to work with a Gazebo simulator, you have to add the ROS control plugin, and also you have to add this Gazebo system plugin. Okay, and this is for the hardware. Okay, so after doing all this stuff, what you have to do is you can write the launch file. So here what we are doing is, here we are starting the launch file called this, okay, Gazebo Classic. So what is happening is that this launch file, don't worry about the like commands and all, just read this heading, that's it. Okay, so like here we are getting the URDF of the robot, then we are starting robot state publisher, Gazebo ROS, this is for spawning the model. Okay, and here we are starting the control manager. Okay, and we are starting two controllers. Forward position controller we are starting here, we are starting joint state broadcaster here. Okay, and starting the RVs. Okay, and we are starting I think these are the things, like here we are starting the Gazebo simulator, then here we are starting RVs. So basically in this launch file, you can actually take this launch file as a reference, and basically it is having like loading the URDF, starting robot state publisher, starting simulation, starting the control manager. It is mostly same as that we have done in ROS1. Okay, So once you start it, if we put GUI equal to true, then you can able to see two GUI, which is Gazebo and Arvis, and then you can simply set the join values. Okay, so that is for controlling a robotic arm. And finally, I just want to run the demo for a wheeled robot. Okay, so that is the final demo. So maybe we can run the diffbot. Okay, there are multiple programs that you can work on. Okay, so in this demo, they are not starting Gazebo and all. They only have the robot, and they are simply, I mean, writing to the hardware. That's it. Maybe I can show you that. So here what is happening is that maybe I can first show you the demo. Okay, after loading it, we can first check the list of hardware interfaces. So you can see we have command interface and state interface, which is, we are basically having two joints with velocity. Okay, we have to provide the velocity for two joints, and 4 state. From the same joint we need to get position and velocity. Maybe after showing the demo I can explain. So what I'm doing is rows topic list, and I'm seeing the command velocity topic and order. Okay, so basically okay, I also want to show you the controllers. So these are the controllers currently running. We are loading differential drive controller, okay, and the joint state controller. Okay, and the hardware interfaces are like, if you want to work with a two-wheel robot, there are two joints, right? Two wheel joints. So we have to write the speed. Okay, that is what it is showing. And these two command interface are actually controlling by the it's actually setting the speed, and this is getting that speed and velocity. So maybe I can just give a command velocity, and you can see the robot is moving. 1 second. I can can see the robot is like rotating, and here you can see it's writing the speed, like got the command 4350, and I'm just giving some other value. So you can see it got a command 1060. Okay, so we can see what is happening in this project. Okay, so you will get an idea. So the example is example 2. Okay, and if you check the description, URDF diffbot, you can see the basic description URDF, which is having links and join, then the materials and the rows to control, and there is a tag called use mock hardware. So if it is, it will set if this tag is true. Okay, so you can see the rows to control. So this is the rows to control. Okay, so here there is no simulation, right? So it's basically loading this plugin. Okay, so if there is any mock hardware, then it will be loading this. If there is hardware, okay, like based on this value, if there is no hardware, this will be loading. Sorry, if there is, yeah, if there is no hardware, the mock plugin will be loading. If there is hardware, this will be loading. Okay, so regarding the join value, like you can see the command interface is velocity and the state will be position and velocity. Okay, and the hardware interface is system. Okay, and you can see the use mock hardware is false. Okay, so if it is false, then it will be loading this. Okay, this is a template hardware interface code. Okay, and if you check the yeah, I think there is that much of thing, like only the control, there is no gazebo specific stuff. And here is the controller controller YAML file. So you have to mention the controller parameters like this. For join state, you can simply mention this. For differential drive, you can describe the parameters like this, which are the joins. It is similar to ROS 1, wheel separation, wheel radius, then all these things you have to mention. Okay, so this will be loading by the controller manager during the launching. Okay, so this is what happening in the differential drive, and you can see in the launch file basically getting the URDF, then starting the controller. So here you can see it is starting the controller manager. Yeah, it is starting the controller manager from the parameter. Okay, like the controller manager is looking for this thing. Okay, if you check this line, you can see it is loading diff board controller. Okay, which is this file. Okay, so basically here you can see all it is loading the controller from this file. Okay, and then robot state publisher, RVs, and here is like individually starting the controller. Okay, so individually loading it. Okay, it is loading diff board base controller and join state publisher. Okay, yes. So if you check the last demo, you can also see the config file. Like if you check it, you can find join state broadcaster and forward position controller. So you can see the description of forward position controller, in which we are using 2 joints and the interface is named. These all are like fixed stuff. You can simply add the joint that you want to control. This is a template. Okay, so if you once more, if you run the diff board, you can able to see it is running it is showing the robot in RVs. Okay, just the RVs, there is no simulation. And if you see the hardware interface code, you can able to see this. Just check the write and read function. So you can see this message. Okay, writing God command in the terminal here. See, writing God command 00 here. Okay, so if I am just giving a command velocity, can see God command 1016. Okay, that is what here, this is what executing now. Okay, So I know there are a lot of contents that we have discussed, but I will say to go through this example. Okay, so basically it is similar to the ROS controllers. Okay, but it got better. I will say the ROS2 controllers got better, mainly in the case of hardware interface, so that you can simply write into the hardware very easily. And there are a lot of examples. Okay, so yes, so you can have a try on this. Okay, and let's see how it goes. Okay, so there are a lot of things. There is a tag called differences to ROS1 control. So there is a detailed differences, and yeah, and it is also giving the supported robots. Okay, so now I think we can have I can take questions. Okay, let me know if you have any question, guys. Like I think I have discussed the important part of ROS2 control and ROS2 SLAM. Let me know if you have any question. I know there are a lot of concepts discussed today, but let me know like if you have any immediate doubts. If you have any other doubts in future, you can mention in the Discord channel.
Thank you, sir. There is no question from my side till now because here 2 a.m.
Okay.
midnight.
Okay. Anyway, we are concluding.
Thank you.
Yeah.
Thank you, sir.
Hari, do you have any questions?
In ROS1, we have a hardware interface.
Yes.
Here it is not there.
Yeah, I mean, in ROS1 also we have hardware interface. In ROS2, there is a hardware interface, and that is what I have shown to you. That this one, these, if you take any example, you can see this folder, right? Hardware. So this is the hardware interfacing code, and which is actually building in the CMake list. If you just check that hardware interface code, see this one. 1 second. Yeah. These CPP code. RR board CPP. So this is the hardware interface code, and that is already given in the example. So that's why I mentioned it got easier. The hardware interface code is already mentioned in the example, so you can easily take the hardware interface code and make the changes. Okay. So basically, if you take the architecture, this resource manager, right? This is actually playing with the hardware interface. And the set of hardware interface available in ROS2 is sensor, system, actuator. And there is one more called GPIO. Okay. And these hardware interface, these writing and reading is actually shown, or it is dealing with this CPP file. And there is a header file as well. Okay. Okay, so I think you can work on the examples, and let's see how it goes. Okay, guys. Okay. So I think we can conclude for today. Okay, I'll inform you like if we have classes tomorrow. Okay, if I am ready with the content, I will be informing you to tomorrow's class. Okay, thanks for attending, guys. See you tomorrow.
Thank you, sir. Thank you. Bye-bye.